Hi, good afternoon or good morning, and welcome to the ZP Developer Zone. Welcome to the ZP Developer Zone webinar on wearables. So I'll go quite quickly. I'm conscious of the time. So when I say conscious of the time, I want to be efficient with people's time. That's always something I want to be mindful of. With that said, let me go forward fairly fast. So today we're going to be talking about wearable sensors and implantable sensors. There will be a sort of ZP perspective on this. You could call it a slight, let's say, bias. But I do have some technology in front of me. Um, these are not our technologies, but I will be talking about CGMs. I will touch upon IVD, in vitro diagnostics, a little bit. I will be talking about wearables and microneedles, a small part. So it'll be quite comprehensive, but it won't, as I say, all be talk. There will be some slides and some demonstrations as well, but all around the theme of wearables. So there's quite a few slides to go through. So let me do that. I'll be talking about sensors, electronics, clouds, and app. I'm at Zimmer and Peacock. We've been developing technologies for in the wearable space for at least 10 years. But prior to that, many of us were actually involved in CGM, continuous glucose monitoring. I will talk very quickly about Zimmer and Peacock. I will talk about trends in the market. Trends in the market now in terms of wearable sensors have actually become implantable sensors. So once upon a time it would be kind of the smallest thing that we would do, let's say, is you'd either see people walking around with CGMs on their upper arm. Um, you may in the next few years see people wearing microneedles on their wrists. But even that now has kind of moved on a little bit because now we actually have people already having sensors implanted into them. And I will touch upon sort of sensionics as one of the case studies this afternoon. So this will be a mix of technologies, and it will also be a mix of a look of back at what's come in the past. So it'll be quite comprehensive, I would suggest. As I say, we will talk about the ZP technology stack. I do have some hardware in front of me, and I will also be talking about configurations. When I mean configurations, you've got kind of transdermal sensors, you've got microneedle sensors, you've got sweat sensors, which is kind of non-invasive, you've got implanted sensors. And I'll also have a case study near the end about Apple, because Apple is obviously trying to use the LEDs on the back of their watches for, well, obviously they're trying to do oxygen, but actually they're also trying to do glucose as well. And I will touch upon, let's say, traditional non-invasive and I'll also be with the microneedles is actually minimally invasive is a better description for it. So there'll be lots of configurations talked about. I'll talk about some implantable biosensor technology from Zimmer Peacock. I will talk about microneedle technologies available from ZP. I will talk about the history of CGM. When I say the history, it's not for the pedanticness of it. It's actually because I think we can prevent ourselves from making the mistakes of the mistakes is a strong word, but we can learn something from the past. Because when I talk about Cygnus and the glucose watch, it's not that they made mistakes, it's just they were they were sort of pioneers in this space. Um, I'll talk about Pendra. People have tried many ways of wearable biosensors. I think every part of the electromagnetic spectrum has been tried. And bioimpedance has been tried in the past, and bioimpedance is being tried even today. People are still trying. And then, as I say, I'll also talk about Apple, who are using the infrared part of the spectrum, though many of their engineers, or not many, but I know some of the engineers on their program actually came from a company called C8 in San Jose, where they were actually using Raman spectroscopy. So why are we here today? Well, I mean, in part, I'm here because actually at Zimmer and Peacock, we happen to have a strong background in electrochemistry. And now, the kind of the grandfather, let's say, of at home point of care, point of need testing is actually glucose meters. Now, that technology obviously has become, you don't need me to tell you this, but it's become very commoditized. If anything, it's now just a sort of, it's not even competition for performance, it's just competition for price. So this is kind of, at least where ZP and many of us in this kind of CGM space have started some of our careers. But that kind of technology now, and this is an Abbott product, so it's not a ZP, certainly not a ZP product. This is the Abbott Freestyle Libre 2. The kind of same science that you would find in a glucose strip is really the same science that you'd actually find in a CGM. The ones that are actually, apart from Sensionics, which is on the market and is functional, that one is fluorescence. The other three, let's say Abbott, Dexcom, and Medtronic, are all electrochemical. So there's been a sort of a shift in the commercial focus away from self-monitoring blood glucose strips more towards CGM. And in part because actually SMBG has become very commoditized. It's IP and intellectual property is not so useful now. It's more about can you meet the price expectations? Whereas CGM, there's still an IP position. It's not so competitive. It does offer genuine improvement, I believe, to diabetics, and there's a sort of there's a bit of a market demand. And to be fair to Abbott, they've also started to prove that there's a sort of a wellness market for sort of metabolic health monitoring. Anyway, that said, I've got a lot to get through, so I want to be quick. This is Zimmer and Peacock. We're not a large company and we're not a small company. We've got a lot of skill sets at ZP, and it really reflects on if you're making a wearable biosensor. You're actually going to require, engineers, electronic engineers, mechanical engineers, material scientists, maybe some electrochemists, maybe some chemists, biologists, and then you've got sort of cloud computing guys these days. You've also got regulatory and also manufacturing engineers. So it takes a lot of skill sets in order to make a wearable biosensor. And CGM, continuous glucose monitoring, is obviously the sort of biggest, not obviously, but it is maybe the biggest application at this moment for wearable biosensors, at least the way Zimmer and Peacock define wearable biosensors. We were launched in 2014, so we're 10 years old this year, and we are ISO 13485, and our business model is we primarily do contract development, contract manufacturing. We do have some standard products for things like in the food test industry, but we make the bulk of our income from helping other people get to market with their technologies. I suppose at Zimmer and Peacock, it's probably worth just saying, we do manufacture in many formats, so we may use thick film printing technology, but at the same time, we would describe that as kind of 2D manufacturing, but we also then have 3D technologies as well, like these micro needles. And so we work in either 2D or 3D, depending on the application, depending on what the market actually requires. At Zimmer and Peacock, we've really been part of this general trending. Even before COVID, there was a sort of push towards decentralization. And when I mean decentralization, once upon a time, blood would be drawn, blood would be sent to a central laboratory, test results would come back. So there was a kind of an intrinsic delay in that. I would say that the reason that we probably have at-home electrochemical testing actually comes from the early 80s. There was I think it's something like the New England Journal of Medicine or something, that there was, before there was at-home glucose testing, especially with glucose strips like the one I'm showing here. Type 1 diabetics couldn't have children, but there was a very small case where a doctor had trained a female type 1 diabetic to monitor her glucose at home, and she was actually able to have a child, and it went to full term, and that suddenly caused a meeting to be called, and a lot of sort of clinicians turned up, and a few entrepreneurs and technical people turned up, and they kind of said, wow, okay, so actually if we can bring at-home testing, we can actually improve outcomes, and type 1 diabetics, for example, can have children. And that was really the catalyst for at-home testing, or at least part of the catalyst for at-home testing. And that was actually LifeScan in those days. This is pre Johnson & Johnson, and LifeScan brought, in those days, it was an optical system for measuring glucose. So there's been a long history in moving technologies from centralized locations, and this kind of shift from centralized locations is being accelerated during COVID-19, but this was something that was going on well before COVID-19. There's been a general sort of, can we do much more, can we do all this kind of testing on benchtop systems, then handheld systems, palm-sized systems, and then it's actually come down to wearables. And so there's been a general kind of, you travel in shrinkage, and actually so much shrinkage. In fact, it now became a wearable system. Again, I would never claim to this was a ZP technology, but these kind of CGMs then is kind of at one point this is where we'd got to. But to be fair, Sensionics, and I will talk about them as well today, have actually implanted sensors now as well. So I think this is an additional now that we're now into the kind of we're starting to come into the world of implantables. And I will cover that a bit today. At Zimmer and Peacock, we have kind of two general platforms, one for in vitro diagnostics and one for wearables. I'd say a third of what we do is actually wearables, and two-thirds of what we do is in vitro diagnostics. I just want to sort of touch on the fact is I do have some of this tech in front of me. So I will do a bit of a demo in a bit, but I will, as I say, I will come to that shortly. So let me just change to here and go forward. So I will talk about IVD, but I will mostly talk about wearables today. Just to say, at Zimmer Peacock, we're a contract developer, contract manufacturer. We do have a technology stack that we kind of describe as sensor to API. So we do have hardware, either in the case of wearables or in the case of in vitro diagnostic hardware. We do have sensors. You can have 2D sensors like this, which is thick film printed, or we also have 3D sensors in terms of wires, like the Abbott Freestyle Libre 3, or 3D sensors in terms of microneedles. Zimmer and Peacock actually have a technology which is covered by 50 patents. It's been 20 million euros invested into it so far. So we do either 2D or 3D. We do have apps if you're so interested. I will send you a recording of this webinar later on. But there is actually an app either on the Google Play Store or the Apple App Store called Sense It All. You can download this app and you can actually find that we've already starting to distribute some of our technology. Now, our business model has not changed. We are contract developers, contract manufacturers. I'd even describe us as kind of OEM, original equipment manufacturers. But our technology, we have a cloud system called Julie. I will do you a demonstration shortly, actually, where I'll do an electrochemical measurement, and I'll show you that the data goes effortlessly to the cloud. The reason that we put all this technology in place is I sort of had a realization, sort of 15 years ago, that we were all reinventing the wheel all the time. And so I was very keen to actually say, okay, right, well, everyone keeps making electronics, everyone keeps making sensors, when really it's the applications that are more valuable. So we wanted to kind of put as much in place as possible. If you look at the technology industry, they're always building upon each other's technology. So there'll be technology stacks, and then at the end, there'll be an entrepreneur who launches a new application on the top of technology stacks. But they don't try to reinvent the whole thing all of the time. But in deep tech, like biosensors, you do find that everyone is actually just reinventing, remaking electronics, remaking sensors. And at ZP, we thought, no, let's put as much as we can in place, and then other people can build upon that technology stack as possible. So we call our kind of technology stack Sense It All. This app is something that you don't have to do it now, because I appreciate we're in the middle of this webinar, but you can scan this QR code and you will find that there's an app on the Google Play Store or on the Apple App Store. And that app is something that drives our electronics. What you'll find is that we have QR codes. QR codes are read by the app that resides on a smart device. That app the QR code tells the app what to do, and the app then programs our electronics. So that's how quickly we can go from glucose to lactate or to ketones, just the use of a QR code. So the app that you are able to install actually is talking to a cloud system called Julie, and you'll see that in action as well. So the technology stack at Zimmer and Peacock is sensors, electronics, apps, and actually all the data is pushed to the cloud as well. And that is really useful, because if you're doing a sensor development effort, sometimes the people using the technology are remote from you, and there's nothing worse than trying to fix problems where you don't have the raw signal. But you will see it in the demo that I'll do today, that actually every time our technology is running, we're always making sure that the data goes to the cloud. It really helps especially in the development phase. but it's also part of the business model. When I say business model, think about your business model eventually. You'll want sensors, you'll want the patch technology probably, and you'll also want a cloud aspect to it as well, because then you can sell the service as well. So the cloud is an important aspect to this. Just FYI, um, in fact, I've got my phone here and it's running the app at the moment. If I scan this QR code, my app has now changed to what we call amperometry. So if you're interested in glucose sensing, for example, or lactate sensing or ketone sensing, amperometry would be super interesting to you. If you're interested in potassium or sodium sensing, or maybe pH, then open circuit potentiometry would be the technology or the methodology that you'd be interested in. If you're doing something more like an immunosensor, then maybe impedance spectroscopy would be interesting to you. At the same time, hydration as well. I mean, impedance is possibly a good technique for also measuring hydration. Um, if you're doing sometimes small molecules, something like maybe creatinine or something like that, then you can use the linear sweep voltammetry. So our electronics are told what to do by QR codes. So you can see how quickly we can actually roll out new methodologies by just generating QR codes. Those are read by the app, and the app will then make Bluetooth connection with the electronics, and that's how we would then program the. I'm just reading some codes on my on here, and that so the app reads a QR code. The app then has the details. It then pushes those to the hardware via Bluetooth. So it means that we can really quickly move between different methodologies and even different tests. So these are some other QR codes. You can practice with this later on or have a go if you want. These QR codes, this one will drive total antioxidative capacity. This one will drive glucose. This one will drive chili. This one will drive ginger. This one will drive potassium. This one will drive pH. And this one will drive nitrate. I think this is just really reflecting the fact that we're here to talk about wearables. The underlying science at Zimmer and Peacock is electrochemistry. Under that umbrella of electrochemistry, there are lots of methodologies, and you choose the methodology based on the analyte and the assay. And then actually, the applications are really kind of there's a lot of applications. You do water testing, agricultural testing, food testing, health testing, wellness testing. So those different analytes that you just saw come up when I said when chili and ginger, you can understand that some of those are foods tests. Glucose could be food or it could be human health. We had pH up there, and pH has got lots of, let's say, applications. Um, so in this particular video here, I'll do a demonstration of this shortly anyway, but we have some hardware. The hardware is instructed what to do by QR codes. The QR codes are read by the app. The app makes Bluetooth connection with either the wearable patch or with the IVD hardware. And then we put the sensor in that matches up with the QR code. So if it's a pH measurement, it's a pH sensor. If it's a nitrate measurement, it's a nitrate sensor. We make sure that we use obviously the right sensor, but you understand, see that in the past, you would imagine that if you wanted to do many analytes, you may be building many systems, but that's really never been the case with electrochemistry. But it's just that people have never understood that actually it's such a powerful technology or technology base that you can actually do lots of analytes with the same hardware. So in all of this, we never change the hardware, even though the analyte keeps changing. We will change the sensor and we will change the QR code. So I suppose there's two variables in this stack. What's the QR code and what's the sensor? Otherwise, everything stays the same. And we're every time we do a measurement, either if it's in continuous or if it's discrete measurements, we are always sending the data to the cloud. Why? Because it really helps us actually supporting clients in the field. And it does open up new business models that wouldn't otherwise been open to you. And when we send the data to the cloud, I actually mean the entire raw signal. And that is a super useful thing, if I can put it that way, because if you want to if somebody contacts you and says, yeah, the glucose technology is not working, it doesn't help you when they just say it doesn't work. Of course, if you can see the signal and you can start troubleshooting, it really does help you sort of find out what actually is the root cause. Just out of interest, in our cloud, we also have an API, an application program interface built in as well. I just want to do a quick demonstration. So what I'll do is I'm just going to change my camera and that'll flick up. Yeah. And I'll stop sharing for a second. So you can probably see my hand moving around at the moment. I'm just going to grab one of our 2D sensors. I'm just going to plug it into the hardware. So this hardware doesn't know what to do, but actually I'm in Bluetooth connection with it using my phone. So I've got the device connected. What I'm going to do is I'm just going to give this test a name. So I'll just call it MJP MJP1. Right. Now I'm going to put a sample onto it. What I do like about electrochemistry as a sort of modality of test is it's really fast. And it does not require super clean samples. That's why I think it actually translates really well into wearables. I think it's one of the few sciences which it doesn't really care whether the sample's clean or not. Let me just make that point for you a little bit by holding this up. This is my sample. Look at that. It's chunky, it's bitty, it's cloudy, but electrochemistry really doesn't care. I can sort of expand, well, I won't expand on it now, but it's one of the few sciences where you don't need super clean samples in order to get signal. It also works in open light like this, so we don't need to shield it, which really saves on engineering. It only requires microliters to actually run, and I'll just do a quick measure, quick run now. And it can actually also be quite fast as well. What I mean quite fast is when you think about glucose strips, for example. Most of the time, these kind of glucose strip technologies, they actually work in about 5 seconds. And that's, really the power of electrochemistry. The particular assay I'm running at the moment, for example, will take, I think it takes about 30 seconds. And then I will essentially get a reading. Just thought there we are. I'm just going to do that. I just did a quick glucose test as well, just to kind of emphasize the fact is these two technologies look very dissimilar, but actually they're at heart the same. In fact, my blood glucose at the moment is 109 mg per dl. I also just did another test alongside this. I'll just change cameras for a second. Let me do that. So what I'm showing here is the ZP technology stack that this app made Bluetooth connection with that piece of hardware, which he called the Sensi-Or. I put a sample on there. The app told the hardware what to do. The hardware ran this assay and gave me the data back to my phone. And at which point now I've got a result on here of, I'm just trying to, of 1300. But I just want to show you something real quick. So let me just share my screen for you for a second. So I'm just going to show you that, in fact, we automatically pushed all the data to the cloud. So let me just do a quick refresh on that. If my computer won't hang, that is. And because what it actually does is, there it is. What it's done is at the same time that I was sorry, when I did the test, it actually sent the raw signal to the cloud. Now, this is just a sort of quite a trivial little test, but you can understand the real impact of this, that if we're working with people who are quite remote from us, and then they're kind of contacting us and saying, this new assay is not working, for example, when you've got the raw data, you can actually go in there and really see what's going on. So I've got my result, which is on the app it said 1300, but it kind of rounded it up. It's 1295. But of course, when somebody contacts you and says, "Oh, it didn't work," for example, this would be a kind of, that didn't work, and then I can look at that and say, "Well, what happened there?" Whereas, this one did work. So it really helps you in the development phase. So when I sort of say that at Zimmer and Peacock, we do sensors, we do electronics, we do apps, and we do cloud. The cloud has a real value to it. I think there's even an API in here as well. There's an API as well that allows us to connect into other people's clouds, and so we can kind of integrate with them. I just want to stop sharing for a second and go back to the webinar. So I just did a quick demo because I just wanted to show you that though at Zimmer and Peacock, we've got the entire technology stack, but I don't want to just be, about ZP as well. I do want to kind of talk about wearables more generally than just, let's say, us. But at ZP, we do have a long history of biosensor development. I think this is almost in chronological order that, the first thing we would have done is glucose and then oxygen and then lactate. And then later on, things like urea and things like creatinine later on. So we do have a lot of experience. And I think this is more of a comment on glucose, sorry, more on electrochemistry, but all of these are all electrochemical assays. It's a very powerful science. So if you're trying to make a decision where you're going to go sort of photospectroscopy or whether you're going to go in electrochemistry, I'm super biased, and I would obviously suggest that you went electrochemistry, but you have to come to that decision yourself. The nice thing about electrochemistry these days is that we can run all of these sort of methodologies actually off very small electronics. Semiconductor industry, I would argue, has actually really got behind electrochemical technologies these days. Things that would otherwise only be lab, for example, impedance spectroscopy would have been something that we could only ever done in the lab. And these days, actually, we can do it on a chip that's smaller than the end of my finger. So thank you to the semiconductor industry for really getting behind electrochemical techniques. The configurations when it comes to wearables, when you think about Abbott and Dexcom and Medtronic, they are using these kind of transdermal wire type sensors. I know some of you online today will be down in San Diego, so you do have BioLink down in San Diego working on microneedles. Today, so far, in the last 4 years, they've raised at least about 158 million US dollars, which gives you a sense of actually how, I don't say hard, but how well funded you do have to be in order to really work on human health and wearables. So microneedles is something that we have. In fact, I've got a microneedle technology here. Zimmer Peacock were the contract developers or contract manufacturers for a company called PK Vitality. Good company, well run. They were in Paris. They did go into liquidation in 2023, and ZP ended up buying the IP then, which is a IP patent portfolio of like 50 patents. So BioLink and ZP probably have the largest patent portfolios when it comes to microneedles. The difference is that they do it for themselves and we do it for our clients. Something that we've definitely worked on is non-invasive monitoring, i.e. sweat analysis. We've done it mostly in potassium and in lactate. And at ZP, we've also done implanted as well. We've done it, you'll laugh, but in fish and pigs. But to be fair, Sensionics have been doing this in humans. I first came across Sensionics 15 years ago. So it does give you a sense of the time it takes to do this kind of technology. I remember finding them and trying to figure out 15 years ago what they were up to. And at ZP, I'll also talk about our own technology as well. At ZP, we do have a lot of components, and components so when I say components, we have 2D printed electrodes, we have 3D electrodes, we have electronics, we have microfluidics, and we have apps. And we tend to bring all this together in order to try and deliver against a client's needs. Like I say, it's a bit of a toolbox, really, because otherwise, it was one of the drivers at ZP was, why is everyone reinventing the wheel? How do we get products to market quicker? And so we ended up just, over the last 10 years, just building up this toolbox. And so, these days we're very fast and very efficient when it comes to getting people to market. But it doesn't negate the fact that you do have to be well funded to be doing wearables. You could talk about doing wearables in the wellness space. We have no connection with Nix, but there's a company in Boston called Nix that's doing hydration monitoring in athletes. That might be a slightly lower bar because they're not trying to make medical claims there. They may be trying to make wellness claims. But if you were trying to make a medical claim, then it's quite a high bar to do a medical wearable biosensor. Just a side note on the electronics, thanks to the semiconductor industry, just because electronics got smaller these days, there's been no loss in performance. So we're living in I don't want to say a golden age of electrochemical biosensors, but it's pretty good at the moment because a lot of technologies have come together. We have worked on non-invasive biosensors. This is something that we did before 2019, where we actually put electronics, sensor, and microfluidics onto one of our guys. and actually monitored him for lactate production whilst riding the bike. And we had a kind of starting state with them. Then we got them to ride the bicycle and start to perspire. And then actually when they started to strain, the lactate came up really quickly. And I think we were really surprised when we did this study, because we're used to, at least my career started in glucose monitoring. So in glucose monitoring, you would ingest some glucose, and like 20 minutes later, you would see the rise of a signal. When in lactate monitoring, actually, we saw the signal really quickly. But I realize now it's because when you go from an aerobic to an anaerobic state, a lot of tissue in the body immediately goes anaerobic and you start producing lactate. So if you're going anaerobic, just say underneath the surface of the skin, it quite quickly shows up in the sweat. So this was sweat data, and I was very surprised how quickly the sensor actually responded. But then I realized because the source of actually that lactate wasn't an ingestion like a glucose would be. It was actually no, this was actually intrinsic, or endogenous rather, from the actual body itself. So it was quick to respond. I was very intrigued by the dip in the data at this time. So I was like, I wonder why we got that dip. And then I was watching a webinar, maybe reading some papers, and this is some sort of Joseph Wang data from UCSD, and he had the same dip. And then I realized years later that actually this is glucagon. Around the liver, you've got a reserve of energy, and the energy sort of kicks in, but it's only a brief second wind, let's say, and it goes away very quickly. And it was very interesting to see that actually in Joseph's data as well. So we were either both wrong or we're actually both right. And I got a suspicion in this case it was actually we were both right. If people ask me, I want to do a wearable non-invasive biosensor. If they ask me, can you do it in lactate and potassium? I'd say yes. And I certainly wouldn't be suggesting glucose because I think it's a tough clinical proof that you'd have to do if you're trying to do glucose, especially for glucose control of diabetics. But I do know people, of course, working on that. A couple of case studies. So I'll talk about an implanted sensor, microneedles, and also non-invasive glucose monitoring as well. So this is something that we do at ZP. This is a package. This is a kind of a transdermal type sensor. What you've got here is a sensor which is the tip of which has got the enzyme on it to make it specific. And the rest of the package contains the power supply, the electronics, and the transducer to get the data out of the sensing package. And we formulate this for glucose and cortisol. Lots of people contact us over the cortisol sensor, but the cortisol sensor is probably one of the most valuable sensors we have. And we work with clients on cortisol, but we never put it on the website. We tried, well, not try. I say not on the website. We don't put it on the web store for sale because the sensor is actually so valuable. But we are working on glucose and cortisol in that particular package. And this shows you the kind of robustness of the technology stack, that this fish is not dead. This fish is anesthetized. It's been, as you can see, it's kind of cut open here, and the fish is dropped into the sensing package is actually put into the fish, and the fish is then sutured back up. And these two fish have undergone that procedure. So the fish are not dead. They're actually swimming around with a couple of glucose capsules in them. And we're constantly monitoring the glucose so that, we can sort of monitor their sort of basal glucose. Then the fish are fed, then the glucose jumps up, and then it starts to kind of trend downwards again. So that's certainly not a Dexcom or Medtronic or Abbott technology, but it has many of those features, except it happens to be in a very difficult matrix, recording in a live animal under the surface of the water. If you're wondering why we're doing it, drop me an email because I will drop you a recording of this webinar later on. But that's something that we're doing at Zimmer and Peacock. We're now translating it into a slightly different kind of capsule, and we're busy putting that into pigs at the moment. So we're working with a client, and the pigs make for a good animal model for diabetics, and we're busy helping that client put CGM technology. I'm sure ultimately they'll want to go human, but at the moment we're doing it into pigs. I will show you some, and I'm sure I'm looking at the names here and I recognize the names, that you're aware of, Sensionics. They've made at this point, I think they've got FDA clearance for 1 year implantable on a CGM, continuous glucose monitor. I've talked the word electrochemistry a lot. To be fair to Sensionics, they're not using electrochemistry, they're using fluorescence. So they have a dye that's got a sort of, it does have a certain fluorescence, but when it binds then to glucose, that disrupts the planarity of this molecule, and it ends up quenching the fluorescence of that particular molecule, and that's their source of signal. It's inserted underneath the skin. First of all, I think it was like 3 months, then 6 months, and maybe they've now got 12 months. It does require twice a day finger prick tests. That could be slightly problematic for them because I think people suggest that diabetics test 4 times a day. I'm pretty sure, I'm not a diabetic, but testing 4 times a day is probably not what people are doing. But with this technology, they need to finger stick test twice a day, and it's possibly because the software is requiring recalibration a couple of times a day. I think have put a hormone on it called dexamethasone to try and stop encapsulation, but I think it does get slightly encapsulated and is a little bit difficult to remove. This is not my photograph. I got this image off Reddit, but it was just interesting that I think these people have had the procedure a few times, and it does lead to, I think, the way they insert it, then they leave behind the sensing package. But I think then it does lead to this slight sort of marking on the skin afterwards. So I'm sure they're working upon it, but that's one of the when I would go around looking for user feedback, this is something I did find out. And as I say, these images are off Reddit. At Zimmer and Peacock, we've got a slight bias that we're quite keen on microneedles. This is, in fact, it's a nicer looking. In fact, I have the sports watch version here in front of me now. So this is a system for microneedle technology. Microneedles, when you look at most CGMs, the transdermal CGMs that exist today, they have these quite big applicators. The one thing about a microneedle that's quite nice is the things like a watch strap or an armband, that's enough, let's say, force to actually bring the microneedles into the skin. So they don't go in as deeply as a traditional. So something like a Dexcom sensor might go 7 millimeters into the skin. These will go a lot less than that. But we were supporting PK Vitality in their journey. Unfortunately, 2023, they ran out of funding, at which point then Zimmer and Peacock did actually pick up the IP, and that's just something now we're quite keen to partner with people who are well funded, who can actually go to the market. The one thing about the CGM space is there are some big players in there, so it is important to have a freedom to operate, and that's why the IP portfolio that we have on microneedles is actually quite a useful technology. I will talk about non-invasive CGM now, so I'm going to give probably 3 case studies. Cygnus, I think it's a Dutch company called Pendragon, and I'll also talk about Apple. So this will be the kind of last parts to this. Just a slide that I put up a few months ago, because at one point then I was really facing a problem with people saying, well, have you got non-invasive glucose monitoring? Because I can pick this technology up on Amazon. I'm pretty sure Amazon have now been clamping down on this a little bit, but the FDA did put a bit of a warning out there that said, technologies that are measuring glucose that don't break the skin are not necessarily reliable. Now that's kind of FDA's sort of claim, but it's just to say that if you do find watches online that say that they are non-invasive and CGM, I think when I look at the audience here, this is scientists and engineers, so that those claims are not true, but the FDA have obviously show a high degree of skepticism. Let's say have shown a high degree of skepticism when it comes to CGM sensors that don't actually break the skin. If you come in late to this, don't worry, I'll be sending you a recording anyway, so no big loss there. So 3 examples of non-invasive glucose monitoring: Cygnus, Pentra, and Apple, and I'll go fairly quickly as I talk now. Cygnus, they really launched in about 1999. You have to give them complete credit for being very groundbreaking in this. I mean, 1999 was, um, I would almost want to say, I think Bluetooth came out approximately in 2000. So these people were really early days. I don't even think that I hadn't had a BlackBerry at that point. So BlackBerry, the iPhone, this is very pre-smartphone. So these people were definitely ahead of the curve in their vision. As I say, it came out in 1999. It was worn on the wrist. Everyone talks about the Gluco watch. I think few of us actually remember what this really was. Um, some of the specification of it, it was giving a reading every 20 minutes. It was worn for 12 hours. It had a warm-up time of 3 hours, and it did require calibration. So people were still having to use glucose meters, finger stick testing, and then tell the watch, this is my blood glucose, and then the watch would probably use that as part of its calibration. Probably worth saying as well that when Dexcom, Abbott, and Medtronic first went to market, they did require you to do something like 4 finger prick tests in the first 24 hours. And they were probably just calibrating the system. Now, I know they've gone calibration free, but they didn't go calibration free from day one. There was something like, Dexcom these days are on, I think they're maybe on Gen 7 of their technology. So, anyway, I'll talk about Cygnus just very quickly. They were using a technology called reverse iontophoresis. I'm sure that many of you have heard this, and so this will be I don't want me to be repetitive, but reverse iontophoresis is you've got the skin, you've got the interstitial fluid, which is what you're after, and they were putting electrodes on the skin and applying a voltage and passing a current, and implying that voltage and passing the current, they were trying to draw ions out through the skin, and those ions were meant to bring interstitial fluid with them, and therefore bring glucose molecules with them. So this was non-invasive, though it wasn't non-invasive in terms of Apple's desire to use the LEDs on the back of the watch. It wasn't that kind of non-invasiveness. They were trying to use reverse iontophoresis. So they were not breaking the skin, but maybe, they were kind of making the skin more porous and drawing the interstitial fluid out. So they therefore had a different circuit for measuring the glucose in that. They were doing what's called a Gen 1 glucose sensor, not super important here. One of the problems they had is it did actually slightly mark and it was slightly itchy, but I will cover that shortly. They were passing quite a high current density on that system and applying quite a lot of voltage. So I suspect that people were going to kind of get little sharp shocks from this system. In fact, I did come across somebody the other day who actually just bought. They were at a trade show and they actually ended up buying a glucose watch off somebody, which I thought was pretty impressive. Only for a couple of $100 as well. Anyway, so it was applying voltage and measuring current. It would extract for 3 minutes and then it would read for 7 minutes. So they're doing an extraction and then a reading. And then they would reverse the polarity. So essentially it must have had 2 glucose sensors on it and 2 extraction zones, and they were reversing the polarity and then essentially repeating the cycle where they would do an extraction and a reading. And I did read online that actually they think they were getting about 50 picomolar of glucose. And when you think that glucose is about 5 millimolar, it means that they're probably picking up about 1 in 100,000 glucose molecules. So they would, it's no criticism of them, but they weren't bringing out, clinically, they weren't bringing out glucose out of the skin in the clinical range. They were actually bringing it out highly, let's say, diluted. That's probably why they had the 7-minute read time, because they were probably doing a lot of integration in order to kind of get the signal up. And then what they apparently did was they would take 2 measurements over a 20-minute period and then average those 2 signals. I did a bit of and then they would repeat the whole process and probably go for some 12 hours. And as I say, it may have actually left people with slight itchiness on the skin. I think what possibly was happening is you could imagine one scenario where somebody was using the technology and actually they were going down in their glucose reading. Let's say over 20 minutes, it went from 9 millimolar to 6 millimolar. Well, the watch was approximately reading that person at approximately 10 minutes, and then they were reading them again at 20 minutes. I'm sure their mathematics was quite more sophisticated than I'm necessarily presenting it here. But understand that if somebody was falling in their glucose level and you made a reading and then you made a second reading and then you average those two readings, you're slightly misreporting what their glucose is at that moment, because in fact you've got a history effect from the previous recording. And so if somebody's true glucose, let's say I measure somebody over 20 minutes and they're falling from 9 millimolar to 6 millimolar, then you may end up with a calculated glucose concentration of 7.3 millimolar, when actually at the time that they get the result, they're actually at 6 millimolar, and that would actually give you an 18% error. And people did report that there was a bit of an accuracy issue. So I do think it's useful to sometimes look at what other people have done. And it's no criticism of this team. These guys were groundbreaking, but it's useful to note that because you wouldn't want to necessarily do that again. The user feedback that they were getting was it was itchy. It had some accuracy concerns. The warm-up period, it had a 12-hour usage, but 3 hours it took to warm up. I imagine the skin, basically the skin had to slightly break down in order for that reverse ontophoresis to work. Different company, different technology. This is Pendra. They were around in 2003. They were on the Dutch market. That's probably why many of us have not actually heard of them. And I think they had an accuracy problem as well. So if you compare them instantaneously to a self-monitoring blood glucose, you may find something like a 50% difference between what the Pendra system was telling you and what a glucose strip was telling you. And then I think they also were poorly correlating with SMBG self-monitoring blood glucose strips. And sometimes they would actually have a serious error. There's a Clark error grid that kind of tells you that you don't always have to be accurate, but it's better to be accurate, but sometimes you can have an error. But there are different classifications of errors. There's class A, class B, class C, class D, and you don't want to be class E. But 5% of the time, approximately, these people were actually giving a class E error, which is quite serious. And so if I was to describe that, that means that you were, for example, saying that somebody was hyperglycemic when in fact they were hypoglycemic. And so they may have taken action in their what they thought was their hyperglycemic state to actually lower their glucose when in fact they were already low because they were hypoglycemic. And if a diabetic goes too low, they can go into a coma. So that would be a class E type error. You can learn something from people like Pendra, and what you can learn from them is that they were actually using bioimpedance to measure glucose. So non-invasive, they were using skin conductivity, which is fine. Electrochemical impedance spectroscopy was a term I threw out earlier on, something I'm very familiar with. They were actually measuring, they think, the sodium levels, and then they were saying that the sodium levels were linked to glucose levels. So that means that their primary signal was impedance, from which they think measuring sodium, and the sodium was linked to glucose. So that means that's a primary signal, that's a secondary signal, and that's a tertiary. So they were very, say, separated from the thing they were actually trying to measure. And that's why they probably ended up with that accuracy. They were also temperature sensitive. Makes sense. Impedance, many materials show a change in impedance just due to temperature. Moisture, sure, if you wear a watch and you sweat a bit and you've got a couple of electrodes on the back of it, I can absolutely assure you you're going to form a short and know nothing about what's underneath the skin. You're just going to know something about the sweat between your watch and your and the sweat. And movement artifacts is probably worth saying about movement artifacts. ZP, we've got a lot of experience in wearable sensors, and one of the things you've got to be very cognizant of rather is when you're waving something around, you can have artifacts in your signal that are nothing to do with, let's say, glucose or lactate or ketone, but actually just to do with the fact that you're flapping your arm around. So they really had a bit of an accuracy problem, and I think that really came from the fact that it was bioimpedance, and the link between impedance and glucose was a little bit long, let's say, in that link. Now, Apple have also been working on CGM for quite some years. I think they bought the IP of a company called Rarelight. I obviously found this online, I think in about 2010. And Rarelight's IP was around infrared spectroscopy. They did work with Rockley Photonics, I believe, for quite a few years. And I believe this is a press release that I found that they're now working, at least in 2023, with TMSC. I haven't recently gone looking for any more material on this, but I know that, at least I can start my timeline on about 2010, and I can at least say at the beginning of 2023 they were still doing this. What they're doing, if you read their IP, is they have essentially they're making almost like a wearable spectrometer, and I mean, not you. If you hold up an Apple Watch, then you will find that there's LEDs under here. So I can understand that they want to shine light through the skin, have it interact with the glucose, and then use the reflectance to analyze whether they've got a glucose signal. I think some of their engineers probably came from C8, which was a company using Raman spectroscopy. And I remember seeing the C8 technology. I don't absolutely know. I don't work for Apple. I haven't worked for C8. It's just what you can sort of figure out on the grapevine, let's say. So Apple seemed to be using the shortwave and the medium wave infrared. I think, not think, but they're obviously trying to put photons in. Those photons are then expected to interact with the glucose, and they get a signal back, and that's what they then have to deconvolute. It's quite hard to measure glucose by infrared spectroscopy. There's a bit of a chemical imbalance between glucose and water, which I will touch upon. Glucose is in 5 millimolar concentration, water is in 55 molar concentration. They might also have a slight quantum problem as well, that there's water is also quite good at interacting with photons and is in quite high concentration. So that might give them a bit of a sort of a bit of a problem, that the water is causing them a lot of interference. But I will touch upon that. This is the infrared spectrum for glucose. So I can understand that when you look at the infrared spectrum for glucose, you've got data that looks like you've got a strong signal at approximately, let's say, 3,500. You've got some fingerprints down at about 1,000 here. So that looks, fairly promising. If I then just show you the spectrum for water, you can also see that water also has a strong absorption at 3,000. But to be fair, it doesn't have the same kind of features at 1,000. So that would give me, if I was an Apple engineer, some hope that I could use this part of the spectrum for seeing glucose against a background of water. But this is a very sort of common drug, and it's fairly representative of lots of small molecules and lots of proteins and lots of enzymes that are otherwise just pumping around the body. So you can see that lots of organic molecules also have an absorption up at about 3,000, and also lots of activity down around 1,000. So when you kind of overlay all of these spectrums, it's very hard to sort of make an argument that there's anything really in the glucose signal that makes it easy to detect it by infrared spectroscopy in a complex matrix. Now, the thing that Apple do have obviously is good funding, great engineers, and they have a good reputation for staying on a program. They do have a slight problem that glucose is actually quite high. 5 millimolar in biology terms is quite high. The other molecule I can think of, which is often quite high, for example, is actually lactate. That can often be in a sort of range of 0 to 10 millimolar. So glucose is quite high, but the background problem here is water, which is also quite high. It's actually 55 molar. So that's a ratio of 1 to 11,000. So water's not your friend. Water is a good constituent of blood, and it's not your friend in this particular problem. And water is good at interacting with photons. It has what's called an extinction coefficient. It likes to interact with photons, and glucose has also got an extinction coefficient, and it likes to interact with photons as well. But I sort of did a back of the envelope calculation, and this is my opinion, and that I think that the signal to noise ratio when thinking about glucose versus water is something like the signal is 1 and the noise is 2,750. Now, that's a back of the envelope calculation, but I do like to do these kind of things to try and understand what the order of magnitude problem that we're facing actually is. So I think they may have a specificity problem, and they may have a signal to noise ratio problem as well. But again, this is Apple. They're well funded. They've got some good, obviously they have good engineers. I'm obviously slightly biased as well at ZP. We do like minimally invasive electrochemical technologies. And, a lot of what I'm saying, and I have to have a disclaimer here, is because we have a patent portfolio on these CGM technology of microneedle technology of 50 patents. So, when I speak, also understand, that that's something that we have, and it is something that we're trying to, something rather we are licensing into customers based on application and based on region as well. Um, so, I might just do a quick summary. So first of all, thank you for coming this afternoon. So I hope I give you a quick introduction to Zimmer and Peacock. Not a big company, not a small company, but certainly a diverse company with the kind of skill sets that it takes to do wearable biosensors. We do have a good history in IVD and in CGM. Um, and our focus has always been electrochemistry. I started my career in self-monitoring blood glucose at MediSense back in Oxford. I spent a good time in California, where there's obviously a lot of CGM going on. We've developed a technology stack so we can kind of rapidly, at least, make a measurement, get that data to the cloud. I did a live demonstration. If you missed the live demonstration, don't worry, there's a recording, and I'll send you a recording. We have worked in all these configurations: transdermal, microneedles, sweat, and implanted. And I also then gave you some case studies of implantable, Sensionics, microneedles ourselves, non-invasive Cygnus, Pendra, and then I made some comments on Apple at the end there. So if you've got any questions, I realize we've gone for 58 minutes and 23 seconds. So I just want to say thank you very much. And I will send you a recording very shortly. But otherwise, have a good day. Some of you, I realize, are in California, but it's getting to the evening here. But I just want to say thank you so much for your time. It is appreciated. It's a valuable resource, and I don't want to certainly waste it. So thank you, and wait out for the recording. Cheers, guys. Take care. Bye bye.